Okay, I'm going to try and explain the solution to problem number 71 in chapter 6, the accelerometer problem. So we have a ball that is on a track, and the track is in the shape of a parabola defined by the function y equals x squared. Um, and we're supposed to try and find a way of expressing acceleration in terms of the x value um, of the ball. Okay, so um, if the ball were completely at rest, if it were at the bottom of the track, there would be absolutely no acceleration, and the ball would be experiencing only gravity and the normal force acting up. Okay, so for the purposes of this explanation, I will be describing the acceleration as the accelerometer is accelerated in this direction. So um, just that's what all my pictures are going to show. And I'm also going to use the idea of this being an inertial reference frame. So the ball doesn't, it's trapped inside of this device and it can't see that it's being accelerated. All it knows is that um, it senses the gravitational force, and when the accelerometer is accelerated, it experiences another force that pushes it up the track. Okay? Um, so in order to talk about the ball at any point along this track, we have to be able to describe um, the slope that the ball is on at a particular location. Okay, so we have to take the derivative of this equation. F prime x equals 2x, right? So, um, so now we know what our slope is. Okay, let's draw a picture of the ball at a particular point along that slope so we can understand what's going on. Okay, here's our um, accelerometer. Here's the ball, and the ball is not moving. Why is the ball not moving? Because the acceleration is constant, and you'll see that in this once we draw the forces here. We have our force of gravity, right, mg, and we have the normal force, which I'm not going to draw all of it because it's going to be really long, as you're about to see. The gravitational force has a component vector perpendicular to the track, and it has a component vector parallel to the track. Okay, and then we have an acceleration, and the acceleration is going to be horizontal because that was the problem that we were given, was a horizontal acceleration, and it will have component vectors that are perpendicular and parallel to the track as well. Okay, so this is our force that's being generated by the acceleration, and the normal force is actually, remember, the normal force is the force that's opposite of whatever it is that's pulling it down into the ground here. And so we have our component vector from gravity, but we also have our component vector from this acceleration. And so interestingly enough, from a geometry point of view, the normal force will be the length from here to here, but in the opposite direction. So I'm not going to draw it in because it would be up and through the page. And why is that? Well, I said that the ball wasn't moving, which means that the normal force has to be exactly the opposite, and its components also have to be exactly the opposite, right? So we have the acceleration going this way, and so we need a force that's exactly the opposite going that way. So that would be the component vector of the normal force. Okay. Anyway, we'll forget about that for now. The reason why the ball doesn't move anywhere in this particular configuration is because the force pulling down on the ball parallel to the track is equal to the force pushing up on it parallel to the track. And if these forces were not equal, then the ball will move into a position where they are equal. So um, whatever the force uh, that's caused by that acceleration is, it will create an upward component vector, and the ball will move so that the angle creates a downward component vector of gravity that's equal to the upward component vector. Okay, so when acceleration is constant, the ball will find a position along the curve and it will stay right there. Okay, that's what we've sort of proven with that drawing. Okay, now we need to think about how we're going to bring x into this equation. Let me draw another triangle and we'll take a look at it. Now, obviously this triangle could be anything, right? I could draw it like this if I wanted to, um, but we won't because we're going to work with this proportion, okay? So we have a slope. That's what the derivative is, right? It's the slope of the tangent line. So the slope is rise over run. So we have 2x over 1. So 2x over 1, and then we have our hypotenuse. Okay? So this triangle can be any size. We could double the size of this triangle and maintain the proportions as of all of the angles and all of the sides to each other, as long as we multiply all sides by exactly the same thing. So whatever, if we multiply this side by 2, then we'd get 4x. But we'd also have to multiply this by 2, and we'd have to multiply this by 2. Okay? Well, this is exactly what we have going on here. Our slope is 2x. 2x over 1, right? We also know that this is theta. We know that this is theta. Okay, and I drew this triangle steep so that you could very clearly see that this is not theta. Theta is over here. Okay, so if these triangles have the same angle in them, with two of the same angles, right? They're a right angle, and then there's theta. Then the triangles are proportional. So this is my short side, and it's 1, and this is 2x, and then the hypotenuse is whatever it is, we don't really care. Not for this particular problem. So whatever I do to this side, I have to do to this side. Well, what is this component vector? Right? It is mg cosine theta. We know that from all the other problems that we've done in this chapter. So if I multiply 1 times mg cosine theta, then I could also say that this side is 2x times mg cosine theta, right? So this is 2x mg cosine theta. But I've also said that wherever the ball is, it's going to, at a particular acceleration, it's going to come to rest at a point when the component vectors parallel to the track are equal but opposite, which means that this also has a magnitude of 2x mg cosine theta. Okay? And now we have our force, we have an angle, and we have another side. So we have 3 pieces of information about this triangle that will enable us to solve the problem. Okay? One thing I want to do is to make this make a little bit more sense. Remember, what is force, right? It's mass times acceleration. So this is mass, and we know that the acceleration is what we're looking for. So we could also talk about this instead of it being F1 or FA. We could just call it a mass times the acceleration. The mass of the ball times whatever that acceleration is that's putting it at that particular point on the curve. So now we have a simple arithmetic problem, trigonometry problem, right? Cosine theta equals adjacent over hypotenuse, and cosine theta in this particular case is adjacent over hypotenuse, so it's 2x mg cosine theta over ma, and that equals cosine. So now I'll multiply both sides by ma, and I get ma cosine theta equals 2x mg cosine theta. And then I will divide both sides by cosine m, or m cosine. So this will just be a on its side by itself, and this equals 2x mg cosine theta over m cosine theta. Cosine theta cancels out with cosine theta. The mass cancels out with the mass. We're left with acceleration equals 2xg. So if you can read a position of the ball in the accelerometer in the x direction, then I will multiply that by 2 times g, and I will give you the acceleration. Okay? So I hope that's helpful.